This topic looks at a different way to describe location of points. We've already come across the standard Cartesian coordinate system, the one that you've grown up on with X and Y coordinates, but that is not the only way we use to describe location. I'm 30 miles southwest of the harbour is not using X and Y coordinates. Move the mouse 200 pixels across and 50 pixels down from the top left corner of the screen is similar to XY coordinates, but again, not quite the same. There is a difference in the way they're being defined. A luxury apartment just 3 blocks east of the Empire State Building. Again, there's some sort of grid system idea going on there, but the units are different and the direction is something that's defined in terms of compass directions rather than an inherent idea of what the left, right, and up and down mean. Check your 6, you might have come across this expression from the military, to look at your personal 6 o'clock position. In other words, right behind you, something's going down. So to start with, see if you can come up with some good ways to describe the location of this point, this little X marked on the screen. How would you describe its location? See if you can come up with a few different ways to do that. And then we're going to talk about the fundamentals of exactly what it means to describe something's location. So if you've got a description in mind, I want you to think about whether it satisfies the requirements I'm going to describe now. I think we always need some kind of point of reference and we need some form of orientation. In other words, you need some well-defined, agreed upon starting point. And you also need some agreed upon idea of a direction. So what are we referring to when we talk about a point of reference? Well, from the examples I've got above, you can see that point of reference in every single statement. If you're 30 miles southwest of the harbour, then you're referring everything back to the harbour. It's assumed that you and the person you're communicating with knows which harbour you're talking about, for instance. If we're talking about the position of an object on a screen, then the top left corner of the screen is the standard origin point, if you like, for most graphical user interface programming that happens. So we would treat that top left corner as being our 0, 0 point, and then we can describe coordinates based on that, moving to the right and moving down. If you're 3 blocks east of the Empire State Building, then we're assuming whoever it is who's looking for an apartment in New York knows how to find the Empire State Building. And the last one, the origin, is essentially the person who's being referred to. So they are their own origin. In the case of Cartesian coordinates, the origin is also called the origin, and we would give it coordinates 0, 0 because the distance from the origin, both sideways and vertically, is 0. And then the orientation, which way you're facing. Well, if we're dealing with a screen, then there is a natural sense of the width of the screen, the height of the screen, the way round that the screen will be held. And with a phone, for instance, that might change. So the top left of the screen will change depending on what your settings are for the screen and which way you happen to be holding the phone at any given moment. And that will affect the way things show up on the screen. But we have an idea of what across means and what down means in the context of a screen that's oriented probably using gravity to tell it which way down would be. We use the same idea in a lot of other situations. We know what down is intuitively if we're drawing on a whiteboard because down is the direction that gravity is pulling us. Southwest, east, these are referring to the compass directions. We have a way of determining uniquely from pretty much wherever we are in the world which way north is, so we can orient ourselves or get our bearings, if you like, directly from that. So let's say this is our origin point for the sake of argument. We've got a little red dot that's appeared on the screen, and if both I and the person I'm talking to know the location of this dot, all I now need to do is indicate the location of my point in relation to that dot. But the dot in itself is not enough. We need to have some idea of which way we're facing or which way we would need to turn in order to be facing the right way. So here's an initial direction. We can think of that origin or pole as our starting point, and we can think of that horizontal line pointing to the right as being our initial line, or what we would normally have thought of as the x-axis. These are, I think, the minimal requirements to be able to uniquely determine the position of something in 2D space. Well, traditionally, we've gone with the grid approach. So you can think in terms of moving in the direction of the purple arrow and moving perpendicular to the direction of the purple arrow. Perhaps you would define turning anti-clockwise to give the up perpendicular and turning clockwise to give the down perpendicular. But that's not the only grid we could use. I mean, you might have used isometric grids in the past, and it might be that the situation you're in lends itself nicely to motion not in just a left, right, up and down directions, but perhaps in 6 different directions. This is the grid that we're going to be using. Bit of a strange one, but this one is a polar grid, which means it should remind us a little bit of a view of a globe from above. So we're looking down at the North Pole, and then the lines that you can see radiating from that, the radial lines, give us some information, but also the circular concentric circles that are going out, they give us information as well. So some of those lines are telling us about how far away we are from the pole, the central point, and some of them are telling us about what kind of angle we are in relation to the purple line. So the standard coordinate system that Descartes came up with, we have an x and y coordinate, and those give us a sense of how far to the right and how far up we are from the origin. But we can describe the same point, the same information, but in a different way if we use this adapted coordinate system. It's called the polar coordinate system, and it uses an angle theta and a distance r. The coordinates are usually written r, theta. So if you have 5, pi, you're talking about a point which is 5 units away from the origin, and the angle turned anti-clockwise from the initial line would be pi radians. In other words, it's going the exact opposite direction to the initial line. Because the polar coordinate system is new to us, and we already have a coordinate system, the Cartesian coordinate system that we're familiar with, it makes sense to spend a bit of time looking at both together and finding the connections between them. Just like we did when we learned about radians after you were already familiar with the system of degrees for measuring angles. Even though a lot of the work we might do with polar curves, we won't necessarily be linking back directly to the Cartesian coordinate system. The whole point of having polar curves and of describing points in polar coordinates is that some things are much more readily interpreted and understood and worked with in this form than they are in the Cartesian form. But we'll begin by getting a connection between the two systems. We've got our x coordinate and y coordinate, and if we change our perspective to look radially, we can see the angle theta, the anti-clockwise angle turned from the initial line, and r, the magnitude of the vector effectively, or the distance of the point from the origin. What I'd like you to do now is pause the video and, looking at the right angle triangle we've got there, see if you can come up with a nice algebraic connection between r and theta and x and y. Off you go. Right. Hopefully you've found something correlated to the 4 results I've got here. These are probably the most sensible way of writing those connections. You can calculate the square of the radius, or the square of the r value, by using Pythagoras, because we've got the hypotenuse of a right angle triangle. We can use tan to link the angle to x and y. We've got to be a little bit careful with that. If you put theta equals arctan y over x, you will find that depending on the values of x and y, you might need to make adjustments from that, just like when we look at the argument for complex numbers. But we can say that tan of the angle is equal to y over x. If we're going the other way, if we have r and theta and we're trying to find out x and y, we can use straightforward right angle trigonometry. R cos theta, which from mechanics would be a bit like resolving a force at an angle of theta, and r sine theta for y, which would be like resolving the force perpendicularly. If you need to convert from polar to Cartesian form, we would use the x equals r cos theta and y equals r sine theta, and it would look something like this. The point 2 pi by 6 means r is 2, theta is pi by 6. If we put it into those two equations, we get x as 2 times cos pi by 6 and y 2 times sine pi by 6. So the Cartesian coordinates would be root 3, 1. Similarly, if we're converting back the other way, we would probably use the other two identities here, r squared equals x squared plus y squared, and tan theta equals y over x. So if I gave you the point root 3, 1, and that was in Cartesian form, you would know that meant x was root 3 and y was 1. Then we could put them together and find the value of r. Generally speaking, we go with the positive square root because we're thinking of r in terms of the absolute distance from the origin. You could argue that using a negative value of r and using a value of theta that was greater by pi radians would also work, and we'll get onto that a bit when we look at curves later. But for now, the simplest option is to go with the actual distance, and then for the angle, we can use inverse tan here. Using a quick sketch will help us to verify that inverse tan of y over x gives exactly the right answer and not an answer that is perhaps pi radians off. And therefore, our final answer is going to be 2 for the radius and pi by 6 for the angle. If you're recognizing connections here with complex numbers, that's good. There will be some close connections made, including with some of the questions in this chapter. You should be able to have a go at a couple of questions already from exercise 5a in the book. You'll be converting Cartesian coordinates to polar in question 1 and converting polar coordinates to Cartesian in question 2. Next, we're going to extend from looking at individual coordinates to looking at the equation of a curve. For example, what if you're given a curve with this Cartesian form, x squared minus y squared equals 4. Now you may or may not know what kind of curve that is in Cartesian. We're not going to look into it now, but if you want to draw it out on GeoGebra, I'd encourage you to do so. But we're going to look at how we can convert this into an equation that instead of using x and y, it will use r and theta. So the only variables involved in our equation will be r and theta, the polar variables. This is how we do it. We see an x, we replace it with r cos theta. We can get that directly from this. And we see a y, we replace it with r sine theta from this one. Well, we can go a little bit further than this. And generally speaking, if possible, it's a good idea to simplify as much as we can. That will enable us to see more clearly what's going on. So in this case, I think I'd be tempted to leave it in this form. It's relatively nice, and if I try rewriting it so it says r equals, then it might lose some of the information that I've got from this format. R squared cos 2 theta equals 4. And if you can find a polar curve plotter online, or if you can watch the video that describes how to use GeoGebra for this purpose, you can verify that these two equations do give the same answer. Here's your next example. What if you're given the polar form and you're asked to find the Cartesian equation? Well, in this case, our curve is r equals 2 cos theta. And often these are a bit more interesting because what happens is we don't have a simple direct way of finding r or finding theta. We know r squared, we know tan theta. But if we can, we need to do things a little bit more cleverly. Often we'll still end up using x equals r cos theta and y equals r sine theta, even when we're going this way around. So the first thing I'm going to do, which may seem a bit odd, but once you've seen it, you'll realize why it's sensible. We're going to multiply both sides of the equation by r. And straight away, we can identify in here, there is something on the right-hand side that looks familiar. It's something that will turn quickly and easily into something involving x. And on the left-hand side, well, we've got r squared. That also appears in our list of identities. So that makes our life very easy. And in fact, if we do that, there's no faffing around with inverse tans that may or may not be perfectly valid. There's no faffing around with plus or minus square root signs or any of that nonsense. All we need here is x squared and y squared equals 2x. And you might recognize that one. Often you would rewrite it in a slightly different form, or even this form, where it becomes obvious that we're dealing with a circle centered at the point 1, 0 with a radius of 1. We'll come back to that r equals cos theta, r equals something cos theta type equation later on as well. I'd recommend you have a go at generating some polar versions of common curve equations for yourself. Try some straight lines. I'd recommend horizontal or vertical straight lines are a good starting point. You might want to try something like y equals x squared, or even a circle equation like x squared and y squared equals 16. Maybe you'll be able to get a sense of which ones lend themselves most naturally to a polar form, and which of them tend to be easy and simple when they're in Cartesian form, but a real mess to deal with in polar form. And then you should be able to have a go at the next two questions in the exercise, questions 3 and 4. Those ones involve converting either Cartesian to polar or polar to Cartesian. Next, we're going to have a bit of an introduction to sketching polar curves. This is where things get really interesting, and there is absolutely no substitute for playing around and trying lots of curves. It will feel, if you're anything like me, very unfamiliar and strange, because the curves and their equations don't seem to connect in the way that you've got used to with a Cartesian system. We'll need to build a new intuition for what the curves are going to look like and how we can sketch them. But I'm going to walk you through a few useful tips, and we'll look at a bunch of different examples. Let's start with this. You already know there's a handful, maybe half a dozen or so graphs that you will immediately recognize if you see them written down algebraically, and you will have some sense of what they would look like if you drew them on a graph. So I'd like you first just to jot down maybe just a word or a phrase, or maybe you can draw a little picture for each of these. Y equals mx plus c, y equals ax plus bx plus c, y equals k over x, y equals a to the power x, x squared out of y squared equals r squared. Those I would feel like are probably a minimal toolkit for dealing with Cartesian equations and graphs. Hopefully you didn't have too many problems with those. Recognizing a straight line, a parabola, an x squared graph. Hyperbola is the official name for this, which you will find out more about later in this course, but you can think of it as a reciprocal graph if you like. The exponential curve, and of course a circle. And if there are any of those where you feel like you're not completely 100% confident you've drawn a valid alternative version of it, try putting some of these into GeoGebra, maybe even with the k values or the a values, and then varying those to get a sense of the family of curves that you're describing. Now, in polar form, there are also a bunch of curves that it's useful to have some sense of. But we're going to start with a few that look simple, and we're going to think about what they mean. R equals 5. So unlike something like x equals 5, where we're saying the distance to the right of the origin is always 5, now what we're saying is r, the distance from the origin, is always 5. The next curve, r equals theta. And it's helpful at this point to mention, when we have x and y curves, you can see from the list on the left, most of the time we like to write them making y the subject. We think of x as being the independent variable, the input, and y being the dependent variable, the output. When it comes to polar, generally speaking, we think of theta as being the independent variable, the input, and r as being the dependent variable, the output. Which means when you look at r equals theta, a good way of thinking of it would be start with theta equals 0, so you're facing to the right, directly along the initial line, and then as theta changes, it gradually increases all the way to pi by 2, so it's pointing straight up, and then you end up continuing to increase theta. You're now at pi, pointing to the left, and then 3 pi by 2, you're pointing straight down, and all the way back to 2 pi, you're pointing to the right again, but then you continue 3 pi, 4 pi, and so on. And as theta increases, think about what r will do. And instead of imagining your graph being traced out as you move a vertical ruler horizontally to the right across your page, as you might do for a Cartesian graph, try to imagine it as being traced out as you move a ray line starting from the origin, pointing to the right, and that ray line rotates around. You'll see what this looks like in a bit. What about theta equals pi by 4? And then finally, slightly weirder one, r equals 1 over theta. What would happen to the radius or the size of the distance to the point as theta gets larger and larger? Well, let's start with this first one, r equals 5. Hopefully you've got something that looks a little bit like this. If the distance from the origin is always 5, then as we trace around, as we go through larger and larger values of theta, r is just coming out as 5 every time. It's like having y equals 7. It doesn't matter what x is, y will be 7. In this case, regardless of the value of theta, r, the distance from the origin, is always 5. So we get a perfect circle with a radius of 5. r equals theta, you might have guessed, does something a little bit stranger. As theta increases, we're going to see this spiral effect happening. And that's because when theta is 0, r is 0. But as theta gets larger and larger, as we turn around, we're also moving away from the origin at a nice regular pace. So the size of the gap between one coil and the next is fixed for any given theta value. But you can see it crosses at 0, at minus pi, at 2 pi. It'll also cross at minus 3 pi. And so those crossing points on the x-axis, if you like, if we call it that, they will be nicely, regularly spaced. Theta equals pi by 4 is not one that you can easily think of as what happens when we put in a value of theta, because the only value of theta you're allowed to put in is pi by 4, and yet nothing restricts the value of r. So this gives what we call a half line. You might have referred to it as a ray before. It's essentially like a straight line, but although it goes on infinitely in one direction, in the other direction it stops somewhere. In this case, it starts at the origin, and any point which has an argument or an angle from the positive x-axis, or the initial line as we call it, any point that has an angle of pi by 4 is a valid point, and any point that doesn't is not. So if you think about all the points along that line, they satisfy the condition, and any point that isn't along that half line doesn't satisfy the condition. R equals 1 over theta. This one's an interesting one, because if you try doing 1 over 0, you obviously get something impossibly huge. So r effectively starts from infinity, and yet by the time we start to see what's going on, theta is already reduced to manageable levels. Theta has got to the size of roughly an eighth fairly quickly, and when it gets there, r will be 1 over an eighth, which is 8. And then as theta increases, r decreases, and it will continue to decrease. So we could continue this on forever. I think I've done this all the way up to 2 pi or possibly 4 pi, but theta could continue to increase, and we would see that spiral just getting tighter and tighter in there. So we had a circle when r equals a constant. We get a spiral, an outward spiral, when r equals theta, or similarly, for some multiple of theta, we'd also get a spiral. And also for something like r equals theta squared, we'd get a spiral-like shape, but it would be increasing outwards more rapidly. If you had the square root of theta, it will be increasing outwards but more slowly. So you can mess with the springiness, if you like, of the spiral. For theta equals a fixed number, you get a half line or a ray. And for something like 1 over theta, where the expression is a decreasing expression, 1 over theta decreases as theta increases, we'll get an inward spiral. You can play around with exponential versions of this, and you can see what happens with logs if you like as well. But for now, this is a sensible starting point. We've got a rough sense of what happens as theta changes. Next, we're going to try a slightly weirder example, 1 over cos theta. I would encourage you to pause at this point and think about the kind of answers you're going to get from this. You might even try calculating a few on a calculator. 1 over cos 0, 1 over cos pi by 6, etc. See what kind of numbers come out the other side. And I've not put a domain down here because I'm thinking of all possible values of theta. When you think you have an idea, maybe try sketching it. If you're anything like me, your sketch will look nothing like the true answer for this the first time you do it, because it won't feel like it's the same. You'll see what I mean in a second. Let's try a little bit of rearrangement. Then you will see a much easier way to sketch this particular curve. If we multiply both sides by cos theta, we will end up with r cos theta equals 1. So our curve is essentially the same as x equals 1. Now what that's going to look like is a little bit strange. You can see it being mapped out as theta increases. It starts from the point 1, 0 in Cartesian coordinates, or starting from the point 1, 0 in polar coordinates as well, I suppose. When theta is 0, r is 1. And then as theta increases, r increases really, really fast. In fact, it's asymptotic. You can see the line shooting up so quickly towards infinity, but it's a perfectly vertical line. And at some point, 1 over cos theta becomes negative. But in between those 2 points, cos theta becomes 0, and 1 over cos theta becomes infinity, or negative infinity, or undefined, depending on how you think of it. So what we're seeing mapped out here is the positive values of r shooting upwards, followed by the negative values of r once theta gets large enough. You might be able to do a similar thing with r sine theta equals 3. If you remember that r sine theta is the same as y, this becomes a very straightforward problem because it's now a Cartesian equation. A similar thing happens with this. We can see for small values we're coming in from very far to the right, we slow down a bit and then we speed up and we go off to the left. So it's very strange to map out a straight line on a polar plot. They're built for curves. They're built for things that are moving in a circular or circular-ish manner. Spirals work really well. Ellipses, even parabolas will work quite well on this sort of graph, but straight lines, not the most natural thing. So in particular, if you've got y equals something or x equals something, you can write it in polar form, but it feels a little clunky and it gives you some weird behavior in terms of when you get the different bits of the line. And there are discontinuities in that because you've got issues whenever sine theta or cos theta equals 0. There are other curves that are essentially, they're in their more natural habitat when we're dealing with them in polar form. Circles is a classic example. It's a little bit messy to describe circles using Cartesian coordinates. We can't even easily come up with an explicit form unless we're using plus minus square root signs. So we often use this implicit version, x squared add y squared equals a radius squared. But the simpler way to do that in polar form is to say, well, the distance from the origin is always fixed, so the distance from the origin equals some number, and that number becomes your radius. Here's an example of y equals x squared. And there are a few different ways to rearrange that equation in polar form, but I've gone with r equals sec theta tan theta because it seemed like the most elegant looking one. If you're curious, you can have a go at proving that for yourself. Y equals x squared, can you use our results to prove that that's equivalent to r equals sec theta tan theta? Again, we get this weird behavior like we did with the straight lines, starting from 0, shooting up to infinity as theta maps around from 0 to pi by 2, and then as theta goes from pi by 2 to pi, we come back down to 0 again. Here's another really nice example of an equation that looks really straightforward in polar form, but looks hideous in Cartesian form. I'm not going to go through the process of converting things like this into Cartesian form in general. I've done this one so you can see, but it's not nice, it's not very meaningful either. If you're curious, this is what r equals 1 minus 2 cos theta looks like. It's not the kind of thing anyone's going to ask you to draw in a Cartesian form, but in polar form it works out quite nicely, and it's the kind of thing you will learn how to sketch. But first we're going to look a little more closely at circles. And this may seem a bit strange at this point, but I'm going to start by investigating r equals sine theta. The reason for this is that sine and cos are cyclic functions. They are functions that are inherently tied up in the way circles work. You might remember that we generate sine squared theta and cos squared theta equals 1 by thinking of the x and y coordinates of a general point that's moving around a circle. Well, we're going to make use of that idea here, and we're going to see what happens if we explore r equals sine theta. First thing I'm going to look at is the kind of values of r we're going to get. Obviously, r is going to vary between -1 and 1 because that's what sine theta does. Next, we've got some symmetry. Now, if you were to draw the graph y equals sine x, you would see lines of symmetry, vertical lines of symmetry at x equals pi by 2 and x equals 3 pi by 2. If we're dealing with r equals sine theta, we'll get the same symmetry, but it'll happen at theta equals pi by 2 and theta equals 3 pi by 2. The next thing to look at is a slightly more nuanced idea. We're looking at the behavior of the graph at different points. So for instance, because the sine wave has a high gradient initially and then a lower and lower gradient as we approach pi by 2, we'll see r increasing rapidly as theta changes at the beginning, that will manifest at the very beginning as a line which is almost horizontal, because r is getting larger very quickly as theta moves around the circle, and then more and more slowly as it approaches 1. Think a bit about what's going to happen after that point, and you might be able to see what's going to manifest with this curve before I draw it out. If you want to give it a go for yourself, now is an excellent time to pause the video, try it for yourself, and then come back. Okay, here is our curve. A perfect circle with a diameter of 1. The value of r increases from 0 to 1 and then decreases from 1 back to 0 again. We can see the symmetry that we were talking about. The line theta equals pi by 2, remember, is a half line starting from the origin. The line theta equals 3 pi by 2 is a half line going downwards starting from the origin. And both of those lines satisfy the symmetrical condition that we were talking about. So the entire curve is symmetrical in both of those lines. As you might imagine, r equals cos theta is going to give us a similar thing. But if you think about the relationship between sine theta and cos theta, hopefully the phrase that springs to mind is a phase shift or a translation of 90 degrees, or even better, pi by 2 radians. We're going to see that in here. Again, r varies from -1 to 1. Again, we've got symmetry, but this time about theta equals 0 and theta equals pi. And then we've got some sense of how quickly the curve is changing. Here is our curve. It has been rotated by 90 degrees from the sine curve. R equals sine theta was a circle of diameter 1, which was symmetrical about the vertical axis, or symmetrical about the half line theta equals pi by 2. This one is symmetrical about theta equals 0, and it is 90 degrees clockwise rotation from the sine one, or pi by 2 if you prefer. The next thing I want to look at is a more complicated curve, and I'll try to show you more thoroughly step by step the process that we follow. So if we've got a curve like this, r equals 2 minus 3 sine theta, and we need to plot for values of theta from 0 to 2 pi, we start with the range. Look at the curve equation and think about the kind of values you'll get for r. The next thing you look at is symmetry. We know about the symmetry of the trig functions. They will often appear in these sorts of formulae, so think about what we already know about those functions. And finally, if necessary, what I call a minimal table of values. You pick out only the values you need to investigate and you plug those in directly to find values of r. So the first question is fairly easily answered. If sine theta varies between 1 and -1, 3 lots of sine theta will go between 3 and -3. And if we're subtracting that from 2, the biggest we can get is 2 take away -3, which is 5. The smallest we can get is 2 take away 3, which is -1. So r will take values between 5 and -1. At the same time, we've got symmetry. Sine theta has symmetry at pi by 2 and at 3 pi by 2. So those are the vertical lines that you can see on the graph. We're expecting a curve which has vertical symmetry through that line. And the final thing will be our minimal table of values. What I'd recommend here, if you've already identified a maximum or a minimum point when you looked at the range, you might say, for instance, we'll get a value of 5 when 2 minus 3 sine theta equals 5. In other words, when sine theta equals -1. And when does sine theta equal -1? Well, that happens at 3 pi by 2. So now we know that the point 5, 3 pi by 2 is on the curve. And we could look it up. We could find it and we could mark that point. And our value of 5 means we're 5 away from the origin. 3 pi by 2 means we've done a 3/4 turn. And we're going to be somewhere like this. We could do the same sort of thing for the minimum value. So we'll get a -1 for r when sine theta is 1, which happens at pi by 2. So that will happen somewhere on the positive vertical axis, if you like, or pi by 2, we're 90 degrees rotated anti-clockwise from the initial line. But it's an r value of -1, which means we need to be thinking about looking this way, but moving a distance of -1 in that direction. So actually our point is going to be somewhere like this. And I'd suggest you try a few other values. Look at what happens at the very beginning. 2 minus 3 lots of sine 0 is just 2. So at the start, when we're looking in the direction of the initial line, we know we're going to be beginning with an R value of 2. Once you've got some sense of where you're heading, then you can start to sketch in your curve. And it's a weird looking one. From the beginning, we head to 0, we head to 0 again, then we reach our maximum at 5 when theta equals 3 pi by 2, and then we go back to the beginning again. The equivalent for polar curves to the standard find out where it crosses the x and y axes is essentially when is r equal to 0, and that's another useful one to calculate here. If r equals 0, we could say 2 minus 3 sine theta is 0, therefore 3 sine theta is 2 and sine theta is 2/3. So whenever sine theta is 2/3, we're going to cross through the origin. And that happens twice. That's where we get this lovely loop-de-loop. The next thing I want to talk about is negative r values. So I'm showing this slightly differently now. We've got a ray line tracing around the theta values as we move along. And we're drawing r equals cos theta one more time, but we're drawing it showing the ray line that represents theta. Generally speaking, there are a couple of different conventions. Sometimes the r values are completely ignored if they're negative, so it wouldn't draw on the sketch anything where r came out as a negative number. But most of the time that I've seen it in most textbooks, etc., and in your course, you'd be expected normally to represent those values of r unless it says otherwise. And that's the way it works in GeoGebra and Desmos, I believe, and other graphing programs. But it's helpful to have in your head whether the bit you're drawing is a positive r value or if it's a negative r value and just in a different quadrant. So you see the grey line that's going around is not always the line that the point is drawing on. When this curve has a green line, it means we've got a positive value for r, so we're moving in the direction of the ray line that's tracing around and around. But if that line becomes red, it means the r value is negative, and we're going back along the line so far back that we go behind the origin, if you like. It's a good practice to think about simple shapes like r equals cos theta, this nice little circle, and to see if you can make sense in your head of which bits of it will be drawn when. So when does the top half get drawn, when does the bottom half get drawn, and which bits are drawn by positive r values and which bits are drawn by negative r values. The next thing I think will be worth trying is r equals cos 3 theta. This is a classic example of a shape that lends itself very nicely to polar coordinates and is a real pain if you're dealing with Cartesian coordinates. Follow the same steps that we talked about before. Think about the range, the symmetry, a minimal table of values. That's where you might try to find out what values of theta we get r equals 0 for instance, and you might pick out a few other interesting points along the way. You might want to think at the beginning about not just the range for cos 3 theta, but how often it hits one of its maximal or minimal points. Cos 3 theta is a squashed version of cos theta. It's a scale factor of third stretch in the x direction if you have y equals cos 3x. So we're talking about a curve that doesn't just oscillate from 1 to -1 back to 1, but it does that 3 times. 1, -1, 1, -1, 1, -1, 1. We're going to see that through the values of r as theta traverses all the way around from 0 to 2 pi. Pause the video and give this a try, and when you're ready, I'm going to show you the diagram on the screen. Okay, here's what we should get. The value of r goes from 1 to 0 and then becomes negative, tracing out a whole different petal, and then positive again to trace out the petal in the second quadrant, going to a negative to trace out the last half of the first petal, and the first half of the first petal again. Then it traces out the third petal for the first time with positive r values, and then negative r values go over once again the second petal, and then we come back to the beginning and finish off. I'd recommend, just like with the r equals cos theta one, you try drawing this and thinking through in your head which bits will be drawn when, and which bits will be drawn with positive values of r and which ones with negative values of r. And of course the natural next question would be what happens with sine 3 theta, or what happens with cos 4 theta, cos 5 theta. And can you make sense of the patterns that emerge And then also the patterns that break. When you try a few of these things, you'll probably have a conjecture in mind, or it's a good idea to think about what you're expecting to see and then see if that's what you actually see. And anytime you see a pattern that breaks, see if you can work out why. The last thing you can do here is the first couple of questions from exercise 5B. These involve sketching. There's quite a lot of curves in there, and there's some really useful examples in the book that come just before this exercise. But if you have a go at a bunch of questions from exercise 5B, question 1 in particular, you'll start to get a reasonably good sense of the shape of these curves and build a bit of an intuition around them. They're fascinating, and you can look them up online and find out all sorts of interesting shapes that you can produce with these equations as well.